So in the previous lecture, we had briefly discussed the relationship of the Lee-Yang H singularity to the directed animals problem, but I was sort of rushed. So let me do it a little bit more detail now. So let us start with one-dimensional nearest neighbor exclusion gas. So you have a line, and these are sites, some of which are occupied, but the condition is that you cannot occupy adjacent sites. Okay, so I can write a Hamiltonian formally for this system, which is summation over I, ni plus 1 plus infinity minus summation ni mu. And I take value 0, 1, and there is a convention that 0 times infinity is 0. Otherwise, I can write plus j and then write, j goes to infinity later, but we just write it directly like this. And then you just have to do omega of z is equal to e to the power beta mu is equal to summation z to the power n of nl. Is the number of ways of putting n points on a lattice of size L, allowed configurations. Okay, so that's easy to do. But suppose I want to do a Monte Carlo process for this model. So there is a Monte Carlo process we will define. Monte Carlo process, which is sort of some time-dependent evolution of this system, and it's odd, even update. So odd even update says the lattice is broken up into odd and even sites. At one time, you update all the odd sites together in parallel. Odd even parallel update. And then you hold the odd sites fixed and update all the even sites. And then you hold the even sites fixed and update all the odd sites and so on. You alternate. So what is the update rule? Well, I have a site and there are two neighbors, and I want to update this site. If one of these sites is occupied, then I cannot do anything because I cannot occupy this. I'm only allowed to update this site, but this has only one choice. You can only keep it 0. So if a site has both neighbors empty, occupy it with probability p, and else do nothing. Okay, and this is independent of what was the status of this site. It may have been occupied or empty, I don't care. I just first erase the current position and then reoccupy it with probability p. Okay? So now, what will happen to this? The claim is that if you evolve, this evolves to the equilibrium state of the Okay, proof. Well, firstly, if you hold the neighbors fixed, then it occurs with, so Z is equal to P over 1 minus P. So the probability that is occupied versus it's unoccupied is in the ratio Z, which is what we want in thermodynamical equilibrium. So what we will say is that you hold the even sides fixed and all the odd sides are equilibrated as much as possible, and then hold the odd sides fixed in their position and equilibrate the even sides. Then from any position you can eventually go to all empty, because with some probability I just empty everything in one, all odd sides in one go, all empty sides in the other go. And so this dynamics can go from any state to any state, and it satisfies detailed balance, so it will go to equilibrium. So this will give me the equilibrium state. Yes? No. Even if both neighbors were empty, it can remain empty with some finite probability. So I am updating the odd sides, I just make them all empty with non-zero probability. And once these are empty, the other ones also I make empty with non-zero probability. Okay? Okay, very good. So now this is good, and it goes into this equilibrium. There is an equilibrium density and I can calculate all kinds of properties. But now I want to have a pictorial representation of this process. And it is convenient to do it like this. This is the t equal to 0 state. This is site 1, site 2, site 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now I update the odd sides. So, okay, to the left of it is nothing, but the 2 and 4 are kept unchanged, but 3 goes to 3 prime. This is 1 prime, this is 3 prime, this is 5 prime, this is 7 prime, 9 prime. And so this is the t equal to 1 state. And this is the t equal to 2 state. Okay, so suppose this was like this. Bad choice. Okay, so then when I come to this side to update, I cannot do anything here, I cannot do anything here. I can occupy this one with some probability, but I cannot do anything at this. Then I come here, both of these neighbors are empty, then I can occupy this one, and so on. Okay? Now this will be called what we call the crystal growth model. This is equal to potassium, I think it spells like this. I'm not sure. How do you spell potassium? Double S. Okay, and this is sodium. Okay, and we say that two potassium ions are big and you cannot put two adjacent potassium ions on top of each other. Okay, so this becomes the crystal growth model. Yes, sir.
Sir, also you write this Hamiltonian.
Okay, That's nice to know. Yes. Yes. Sorry, Sujit, is it important that you say this now?
Oh, sorry. If you wanted to.
Yeah, I mean, it's okay. I mean, I just, since I have a finite amount of time, and okay, so now what we would like to do is we will like to calculate what is the probability that in a particular steady state, if I go to a site very high up, when the system has reached equilibrium, then it is n equal to 1. So when will it be 1? Well, I want this to be 1, then the things below should be empty. So this is equal to P times probability that both downward neighbors are empty. Okay, sorry. And this is equal to P times by inclusion exclusion 1 minus probability that this one was occupied or this one was occupied. So probability that the one downward neighbor is occupied. One occupied, one given. Occupied. And then there are two of them, but probability both occupy. And this we wrote, this is P into 1 minus 2 times this same function, because it's in equilibrium, it's the same state. So this is probe of n equal to 1. But this is a new one. It says two adjacent sites, adjacent on this odd lattice, are occupied. So this is probe of what I'll call 1, 1. But now this probe 1, 1 is a new object. So I can ask what's probe 1, 1? That will be that, I want these two sides to be both occupied. Then all the three downward neighbors of this must be all empty. So this is P squared into all three down neighbors empty. And so this becomes P squared 1 minus, any one of them could be occupied and that will not work. So this is 1 minus 3P probe 1. But then I have overcounted, so I should add probe that two of them are together occupied, and this can occur in two ways, but they could also be probe 101. But then I have overcounted, and so I write probe 111. So this is something before, this is the same as this, but these two are new objects. Probe 101, probe 111. So I will write similar equations for these, and so on. So there is an infinite hierarchy of such recursion equations. Okay? This point is quite clear? Okay, very good. So now we come to this problem of directed animals on a square lattice. So we defined the problem that you have a lattice. There is the origin. An animal is a connected cluster of sites. Okay, where from any side there is a path to the origin using only occupied sites and going down or left. So you start with the origin, you occupy a site just above or just to the right of an occupied site and keep on doing this with n particles. And how many distinct configurations of the board can you get? That is the number an. An is the number of occupied sites, number of clusters of within occupied sites. And then we said that an is equal to 1, 2, 5, 13, 35, 4, n equal to 1, 2, 3, like that. Okay? And then we define a of x is equal to summation an x to the power n. This is a function of x, it's called the generating function. And if I can determine this generating function, then I have essentially determined all these an for all n by Taylor expanding the function, I can determine them and vice versa. So can I determine this a of x? So a of x is, as we wrote last time, I can start with this site and sum over all animals to the above it. And this will be called a of x pictorially. Starts with one site and sum over everything to the right. Then we have this equation a1 of x is equal to x, because this site may be occupied and nothing is there after it, so that is just x. But maybe this site is occupied and there is one site above and this site is not occupied and there is a cluster like this. Okay? Or you may have something like this where this site is unoccupied and there is a cluster like this. Or you may have both of these sites occupied and there is a cluster like that beyond. Okay? So actually let us write it like this. I'm writing the same equation but in a slightly different notation. So this is just a single site. All these are clusters of the site which start here and look like that. These are clusters which look like that. These are clusters which look like that. And the weight of this is 1 plus, this is A1 again. This is A1 again. And this is A11. Because these two are occupied and this is the cluster occupying them. And then similarly I write equation for A11 of x. So, yes. A subscript 1 is that there is a line, there is a single site occupied and a cluster grows out of this. Okay? Sorry? Is the generating function for the number of animals. The source is denoted by the subscript. So if the source is two sites occupied, I denote it by 1, 1. If the source is like this, then I denote it by A101. Okay? So A11 will be, you have to start with two sites occupied on a line, and then what happens? Well, maybe nothing is there afterwards, or maybe these two sites have one site here on the next layer which is occupied and then there is a cluster with that. Okay? Or maybe, and this site can be in three places. So there is a 3, but these two sites maybe there are 2 sites occupied, and then there is a cluster after that. But this can be done in 2 ways. Or maybe these 2 external sites are occupied, middle one is empty, and then you form a cluster with that. Or maybe all 3 are occupied, and you form a cluster with that. Okay? So we write here equal to A 1 1 equal to the weight of all these animals. In each case you write x squared. This is the weight of these 2 things. 1 plus 3 A1 plus 2 A11 plus and I kind of get a feeling of deja vu because I have seen the same equation before. The counting is more or less the same, except there are some negative signs. That's the only problem with this difference in the two equations. Okay? So it says that suppose I put a negative sign with each odd number of, whenever there is an odd number of particles in A, then I put a even sign. Whenever there is a even number, whenever there is an odd number, I put a minus sign. Whenever there is an even number, I put an even plus sign. Then these 2 will be the same. So, or let us say by inspection, probe of C is equal to minus 1 to the power C A of x, A C of x equal to minus P. You make this equivalence, then these 2 equations, this one and all the subsequent one becomes identical. Because the minus 1 to the power C is minus 1 to the power number of ones in the source C, and that will exactly produce all the minuses in the suitable place, and then the 2 equations are identical. Okay, so this is the equation. Probe C, this is the probability that on a one-dimensional line I have a particular configuration of ones and zeros. That is a problem which I can easily do because that is a one-dimensional some StatMech problem done by transfer matrix or whatever method, right? So I know this one, and hence I know this one. In particular, if I just want probe n1 equal to 1, this is what we wrote, this is the same. Probe C equal to just one occupied site. Then this is the minus density of occupied sites in the crystal growth problem / NNE gas problem. These are the same. Okay? So there, of course, I know the partition function. We worked it out last time in terms of some square root 1 by 4 plus z something. So I know the expression for rho. So I know A of x is equal to 1 by 2 plus square root 1 minus 3x okay, just substitute and this is what you get minus. So it has an explicit formula, then you can expand it and you get an goes like 3 to the power n over n to the power half for large n. And so we can solve the 2D animal problem because we can solve the 1D lattice gas model. Okay? Now I would like to show that, oh, this correspondence is valid even in higher dimensions. Okay? So, yes. So suppose I consider a d-dimensional hypercubical lattice. Hypercubical lattice. So for my convenience, I like this to be a body-centered hypercubical lattice. So what is a d-dimensional hypercubical lattice? Looks like, well, I cannot draw pictures in high dimensions very well, but you know, this is the 3-dimensional one. And the BCC says there is also one particle in the middle of this cube. And the 4-dimensional one is the same thing. You first draw a 4-dimensional cube, then put one particle in the center of the cube, 4-dimensional cube. And then repeat this all over. And the nearest neighbor bonds, this side is connected to 4 sides below and 4 sides above. Okay? So now, that is the hypercubical lattice, and there is a d-1 dimensional body-centered hypercubical lattice, which looks like this. You just kind of project this down, and in my case, it looks like this. Okay? It's also a square lattice if you look carefully, because you know the circles will form a tilted square lattice. But I'm calling it body-centered square lattice, which is allowed. Okay, so I take a nearest neighbor exclusion gas on this lattice. On this lattice, and I put a weight Z, and I want to consider the thermodynamic equilibrium state of this gas. And I will do exactly the same Monte Carlo, odd even update, parallel update of all odd sides, parallel update of all even sides. So if all these sides are empty, then I will occupy this with some probability. Then I will take all these 4 neighbors, and then if all these are empty, I will occupy it with some probability and keep on going like that. And they'll produce the equilibrium configuration of this. Okay, so there will be some equilibrium density for any given activity. So given this gives you the density of occupied sites. Is the rho is the density, let's write density rho, and then I write d-1 NE gas with activity Z. Okay? But now let me try to imagine directed animal problem on this 3-dimensional lattice. Okay, so there is a site, it has 4 sides going up. So the direction is upward. So every side can be occupied if there is one thing below it which is available, which is occupied already. And so when I write the generating function for all animals starting with this, there will be 4 sides above. So there will be a term corresponding to only nothing is occupied, or 1 is occupied, or 2 is occupied, or 3 is occupied, 4 is occupied, and all possible ways of doing it, and that's the term. Then there is 2 and 3. But now the same equivalence which is given here. Now I ask, what happens in the Monte Carlo algorithm? If I come to a site, I say, what is the probability this is occupied? Well, all the 4 below it must be empty. So there is an equation P multiplied by probability that all 4 downward neighbors are empty. Okay, then that will be 1 minus probability that 1 is empty, 2 is empty, 3 is empty, with plus minus signs, and it will give you an equation like this. And the animal problem will give you equation like this, and these 2 equations are the same. So this result holds in general in D dimensions for the BC, this hypercubical body center lattice we showed. Then you can take some other lattices and similar arguments go through. So this result is true in general. So this is equal to A of D-dimensional animals, D-dimensional directed animals, and I got to put x is equal to z over 1 plus z. Because I got to occupy with this probability, that is the weight x, right? There is a minus sign that takes care of the minus sign. Those are just kind of details. But then there is a very interesting and very powerful result. It tells you that this animal counting problem is the same as the problem of determining the density of this hardcore nearest neighbor exclusion gas. Such equivalents are known, one model can be shown equivalence to another model quite often. But here there is an extra subtlety or surprise, which is that this problem is in D dimensions, and this is in D minus 1 dimensions. So there is a D-dimensional problem of counting animals on a 2D lattice that becomes a problem of doing something or the other in a 1-dimensional problem. So this is called dimensional reduction. So directed animals in D dimensions. Is equivalent to Yang Li and the hardcore model in D minus 1 dimensions. So these models are characterized by this Li-Yang H singularity, which is the singularity closest to the z-axis, z origin in the z plane, and that occurs at negative z, and so the corresponding animal problem is with positive weights. Okay, so the exponents of the hardcore model, the Li-Yang problem, can be related to the exponent of the animals. For example, in the edge singularity, we had the exponent which characterizes the rate at which the density of zeros goes near the edge. So it was, so here it was density of zeros near edge in Young-Lee problem goes as epsilon to the power minus sigma. Okay. Just 1 minute. Minus sigma. It's okay, it's a definition, maybe it doesn't agree with all the definitions given in other places. And in the other problem, number of animals, number of directed animals of size n goes like lambda to the power n, n to the power minus theta. So these two exponents are related to each other. Because if you know one, then you can determine the other in all the dimensions, whichever dimension you take. Yes, sir. You know, so then there is a general treatment, but there is an additional fact which I mentioned later, which is that, so in the Young-Lee problem, there are zeros, lines of zeros, and there are n points of the lines of zeros. Near the n points of lines of zeros, sometimes the density of zeros goes as a power, and this power is universal in that dimension. For a particular dimension, it always takes a particular value. And that value we are calling sigma, okay? And this sigma is related to this exponent theta, which counts the number of animals in some way. Yeah, so, So, okay, what is the Young-Lee edge singularity? Let us call it edge singularity. The Young-Lee problem will be characterized the edge singularity because that is the most interesting point about it. Okay?
Animals.
Yeah.
When you look at the 2D
Yeah.
and look at the Young-Lee,
Yeah. Yeah.
So is that known as that?
Yeah. So
known,
the 2D, it is known that theta is 5/6 and sigma is 1/6. Okay, so the relation is 1 minus 5/6 is 1/6. Okay. Now it turns out that this result is even more powerful than this, and there is another problem in d+1 dimensions, which is also equivalent to the same Young-Lee problem. So let me write down the statement and then we will say something about the result. So number of undirected animals in d+1 dimensions goes like lambda to the power n and to the power minus theta prime, and this exponent is actually the same as this theta. So undirected animals are where you don't put in the directed constraint, you just have clusters of n sites and you count all of them. And that problem actually becomes reducible to a problem in 2 dimensions lower. So if I can solve the edge singularity problem in 2 dimensions, I can get the critical exponents of the animal problem in 4 dimensions, which is one of the few models where the non-trivial critical exponents in 4 dimensions can be determined. Okay, it's not the only one, but okay. Now, the proof of this result is a bit complicated. The original arguments involve something called supersymmetry, which is kind of a complicated and subtle concept, and converting it into a result involving enumerative combinatorics, where you just count things, is very hard because it involves subtle field theory arguments and operator algebra. There is a proof which is due to Bridges and Imbri. They gave something initially, but they improved the proof. Annals of Mathematics. Annals of Mathematics. 158, 2003. (1059). 1019. This one is somewhat simpler. It involves more or less, doesn't involve explicit statement of supersymmetry, but it still involves continuum formulation. So you have to put the animal problem in continuum, where the positions of the objects can be continuous, and I have not been able to convert it into a problem involving only counting. And so I will not do this here because I don't even understand the proof honestly fully. I've read it, but I don't understand it. But I refer it to you because maybe you can. Firstly, the result is very powerful. So let me write the result in some simpler notation. Yang Li in d-1 dimensions is equivalent to directed animals in d dimensions is equivalent to undirected animals in d+1 dimensions. So this is a dimensional reduction even by 2 or 1. Yes, sir.
So my recollection is that the animals problem has the analog of the free energy violates hyperscale.
Yeah.
There's a dangerous irradical variable. And then for the Yang Li, is that still true? Is that part of the
So since these things involve complex Z or negative Z, so some of the things like free energy, convexity properties, etc. don't hold.
But there's a function that scales.
Yeah, so it is the generating function A of x, or equivalently the free energy. They scale like sigma to the power, that power of sigma comes directly from simple integration of the log potential. So that works. I'm not going into, the hyperscaling involves sizes of particles. The sizes are, this has 2 sizes, one is longitudinal size, one is transverse size. The transverse size works okay. The longitudinal size is not so well understood or known.
So for the renormalization groups that you do, there's an obvious irrelevant variable. That's it. It doesn't come into the negative problem. It's just basically a complex.
So the renormalization treatment of this problem is problematic. So, and I don't understand it. Because the renormalization involves, the directed animals problem is anisotropic. So there is a, so you have to rescale in different ways in different directions. And so the renormalization is tricky there, let me just say. For the undirected problem, the equivalence to the Yang-Lee problem itself involves that thing, and that is the part which I don't understand. So that is the tricky stuff which remains to be sorted out. Okay. Okay. So I think I will stop here for this problem, and the remaining time, which is about 30 minutes, I want to discuss coming back to phase transitions in hardcore models in 3D. In the previous lecture, we only discussed mostly 2D problems. So now I want to discuss 3D problems. Yeah.
Kind of similar to this from like d-dimensional stat-mech problems can be reduced to d-1 dimensional quantum. Is some sort of...
No, because d-1 dimensional quantum problems are actually the same. It just there the change is just in name. There is no actual computational advantage. But here there is actually a computational advantage. You can solve the lower dimensional problem more easily by different techniques.
But even there like 2D Ising model and then you get transitive Ising. It is easier to...
No, so Onsager solved the same thing without using quantum mechanics, but was basically using the same algebra. Okay, I mean he didn't call the operators Lipschulz lattice Fermi operators, but it was using the same technique. So I think there was no I don't think the problem becomes easier because of this. The problem becomes easier because it's a free fermion problem, you know, some other property of the model, integrability. In general, whenever you have Monte Carlo process which evolves to equilibrium, if you look at the history of the process, that is a d+1 dimensional problem. But if you look at the steady state, that's of the Hamiltonian which is d-1 dimensional. So this one is sort of like saying that if you, or it is a special case of this point, that a time-dependent Monte Carlo history is a d+1 dimensional process, but the equilibrium state is a d-dimensional, and you know the correlation functions can be functions of d dimensions. Okay, so now is that hardcore models are very interesting in all dimensions, 3, 4, 5, whatever is your favorite, 21. Okay, so let us consider hard rods in 3D. So this thing is an unabashed advertisement for a recent paper we wrote. So this is N. Vigneshwar. One 3304. Okay, so what happens to hard rods in 3D? We have not made great deal of analytic progress in this, but using this Monte Carlo technique which I described in the previous lecture, we can actually do rather good simulations and we can see what happens. So what happens? So you can take k-mers, where k is the size of the chain, and it turns out if k is less than or equal to 4, there is no transition. So this is a lattice. Yeah, it's 3-dimensional cubic lattice actually. I think the lattice, for the questions we are asking, the lattice is hopefully not very crucial and other lattices will behave similarly, but we have not tried other lattices. So if you have k equal to 5 or 6, So there is a phase transition. What would be the phase transition of hard rods in 3D? So you might guess that there is a nematic order, that's what Onsager said. But Onsager was working with very long rods, and these are not so long, so it turns out there is no nematic phase. So there is one phase transition from something called isotropic phase to something called layer disordered phase. And this is first order. There is a jump in density when you work in constant activity ensemble. So what is this layered disordered phase ordered? So layered disordered phase consists of all the rods kind of lie in some planes which are parallel to each other. They can take three orientations, but the number of rods in the, let us say, Z orientation will be very small. In a typical, it will be there, but it may be, so there is densities rho 1, rho 2, rho 3, or rho x, rho y, rho z, and what one finds is that rho x is nearly equal to rho y is nearly equal to half, rho z, or it's some number, rho z is nearly equal to 0. Okay, so within the layer there is no nematic order, but there is a selection of orientations, and one of the directions is not taken. Yeah, of course it can be. There is a spontaneous symmetry breaking. It can be any one direction. Okay. However, if you go to k bigger than equal to 7, then there are two phase transitions. So it is isotropic, goes to nematic, goes to layer disorder. Okay, so this is this one, of course, kind of expected, that is what Onsager had discussed. But then the next transition is occurs at high density. If the density of nematic phase is very high, then since the nematic order is quite strong, they are more or less parallel, but there are spaces between them. So anyway, all the rods are aligned in one direction, so they are kind of in a layers. You can say they are directed, but they can also be thought of as lying in planes. However, within the layer, you have rods like this in nematic order. But now these are kind of parallel, and you can take k parallel rods and flip them together to form something like this. And this process becomes very efficient, or it can happen quite often if the density is large enough. And so at high density, you get large number of these stuff, and then eventually the number of these becomes equal to the number of these, and there is no nematic order. Okay? So I guess the point is that for nematic order to come, k has to be sufficiently big. And 7 is, let us say, the magic number. And so less than 7 nematic order is not possible. But this layer disordered phase is still possible or happens. Okay, so actually experimentally when we did Monte Carlo, we found something in between these. One more phase. The phase was very interesting. The system broke into layers. In one layer it will be ordered in the x direction, in the other layer it will be ordered in the y direction. And these, within a layer it was nematically ordered, but different layers were not correlated with each other. They were kind of independent and they could be oriented in whichever way. And this phase is seen in a moderate range of densities between these two. However, there is a theoretical argument which says that this phase is unstable. It is sort of thermodynamically unstable. If you take a big system in which you have something like this, no, these layers are parallel, the next one, and there is a next one. This one is parallel. So this one can be either horizontal or vertical. Sorry, either in x or in y direction, I beg your pardon. Either like this, or they could be all ordered like in the y direction. This is x, this is y, and this is z. Okay? However, if you put them in the x direction, parallel to both of these, then it turns out that you lower the free energy, because then all these things are kind of parallel. And if k of them are parallel, then they can be flipped together to form vertical. So you have many more possibilities. Okay? So there is an effective interaction which is aligning between layers. And that is, the amount of interaction is proportional to the area of the layer. So if the area is large enough, it should become important. The entropy gain here between this and this state is just log 2. It is not proportional to the area. And so even a tiny free energy gain in area will swamp the log 2 gain in entropy. But in our systems which we studied, the coefficient of the L squared term is sufficiently small that this log 2 term is important enough, and you see it. And it takes long time for these states to flip to that one or vice versa. So in experiment, you see this intermediate stuff, but theoretically we have a convincing argument to us that it's a metastable state, it shouldn't be there. So there are only 3 phases like this. One, yeah. They are just parallel planes. Okay, so that is what happens. And so if I work in higher dimensions than 3, what will happen? So our guess, which is based on just prejudice, is that this is exactly the same. You will expect exactly the same transitions in any higher dimension. The number at threshold at which something else happens can change, but if the rods are long enough, at low density you will have this phase, at high density you will have this phase, and intermediate density you will have this phase. Yes, sir.
So if you have a layer that's like that,
Yeah.
there must be some communication.
Yeah, so the communication occurs like this. So there is a layer like this, and there is a layer like that, and another, and there are k of them, and all of them are parallel. So once in a while I can find a set of x layers, x rods, which are on top of each other in the z direction. And then these can be flipped to make it like this, which gives you,
So what, is that vertical now?
yeah, those are in the z direction.
Normal to the layers?
Normal to the layers. So this occurs very rarely because k of these have to be aligned, but it can occur with finite probability, and that probability leads to this state being favored over this. This occurs less often, clearly, if these are perpendicular. And so this state is favored because it leads to more states connected to it.
But they can cannot exist without having something.
Of course they are there. So there is a small density of vertical layers which is actually proportional to k to the power minus k. But so it's still a non-zero number, and eventually for large enough areas it will win out, and it will lead to preference of this over this. The argument that in the two-dimensional system will not be nematically ordered is the same as what we presented earlier, that there are only two nematic states, but if you flip them like this, then there are many more states. So at high density, certainly you don't get nematic order. So then this is the simplest option, is that the system can still break into two-dimensional layers, each of which is disordered within a layer, but then all the other layers are disconnected, roughly independent. Okay, so now in the next 5 minutes, so these in the continuum limit is complicated because the size of shape of the cross section may be important in going to the limit.
But then you would expect
so here the smectic phase is not there because the thickness of these in the you can have smectic, but that you can call this the smectic phase,
But that could be in the Z.
So the layers are in the perpendicular to the z-axis. All the layers are perpendicular to the, let's say, called the z-axis.
That you don't see.
No, that's what we see in the high density. All the rods are perpendicular to one particular direction, but x and y are equally likely to occur, or equal density.
It's periodic. Right, left,
No. Within a layer, I had shown some, maybe we can. You have rather complicated structures which there is no long range order within the layer.
So within the layer you have both directions.
Within the layer you have both directions and there is no long range order. Okay? Sorry? Correlation length tends to be quite large. In the cases we have studied, these are like k equal to 7. The correlation length can be at least 30 or 40, several times our system size is only 60. So we are treading on thin ice, but correlation lengths are large. They are even in the z direction the layers are nearly independent. They don't care. Most of the number of, so here let us say if density is 0.95, density is 0.8, rho z will be 0.001 and all the other rods will be in the xy plane. It's very low. The z component of the rods which are present is very, very low. All the other rods are in xy and they are equal in number. Okay, so in the next 3 minutes now, I have to tell something about the phase transitions in 2x2 cubes. Two by two cubes on the cubic lattice. Okay, so again, there is a low density phase which is disordered. Then if you increase the density, you go into a state which is layered, which breaks the symmetry in one direction. Let us call it z direction. So things will occur in, these are 2x2 cubes. They lie on one constant z plane. And then the next stuff lies on the plane separated by distance 2. So there are thickness 2 slabs in which most of the cubes lie. And in between these slabs, there are very few cubes. But within the slab, there is no long range order. Okay? But then, if you increase density, they become sublattice ordered. Where there is one of the 8 sublattices is selected, and it's a periodic arrangement, it's solid like crystalline structure. But then if you increase the density even more, this goes into columnar order. Where the system kind of breaks into 2 by 2 pipes. There is the next pipe. Within a pipe, the squares can slide vertically. But different pipes are uncorrelated more or less with each other. And there are very few cubes which occur between the pipes. In principle, there can be something which lies halfway in one pipe, halfway in another pipe. That fraction is very, very small. Okay? So the details of the stuff is very hard to understand, but qualitatively, this thing is disordered. This breaks symmetry in one direction, z direction. In the xy direction, there is no symmetry breaking. This breaks symmetry in 3 directions. And this breaks symmetry in 2 directions because the pipes are arranged in, let's say, xy plane with equal spacing. So it's a very counterintuitive stuff because first time you break some symmetry, then you break even more symmetry, then you restore some of the symmetry. It's very non-monotonic. One would have just guessed that, yeah, first you break one, then you break another, and then you break all 3. So you would have liked that this order is reversed, but it doesn't happen like that. And understanding this point, qualitatively even, from first principles, seems to be non-trivial. We haven't achieved that yet. So now my time is, 40 seconds remain, but 40 seconds is, this is some problem with this, no? 15 minutes. 15 minutes, then I can tell you more about this. What more can I tell? So, why is the sublattice order unstable at high densities? The argument is again back to the same. We said you create one, suppose you start with perfect crystalline order in which all the cubes are packed in a periodic array. Then you remove one square. Then you create half defects. You can slide things along a column and you create half defects. And these half defects make the sublattice ordered state unstable. But of course you can create them sliding defect in this direction and another defect in some other direction. But then if you have a large number of such things, then these pairs of defects tend to be aligned with each other and they form a nematic phase, and that is the columnar order. Okay? But now if you have lot of such defects, then it is said, these are the words people use, the small number of defects destabilize the sublattice order. That's what I argued just now. But if you have large number of defects, then the columnar order is, they stabilize this against the columnar order. So, you can give the argument whichever way you like, but small number of defects tend to give you columnar order. If you have more defects, then you restore the sublattice order, which is very counterintuitive for me. Okay? So even the qualitative behavior of the phase diagrams, even for the simple models like 2 by 2 by 2 cubes, what could be simpler than this, is not easy to understand. Okay? So if you take more complicated objects, which can be cuboids, but unequal shape. They may be brick-like stuff. Then you get additional phases possible, which are called smectic phases, where there are layers. But within layer, there is actually a breaking of translational invariance or not breaking of translational invariance. So, you define all these orientational order parameters, translational order parameters. There's some complicated coupling between them. Then we tried to write some Landau theory for this stuff. And it turns out that the naive Landau theory, which you write down copying from standard textbooks for this problem, that fails completely. Because the naive Landau theory does not accept the columnar order. It's always less stable than the sublattice or vice versa. So it's hard to accommodate the columnar order in a naive Landau theory. Of course, that is overstating the stuff, because Landau theory is known to be wrong anyway in detail. So let me recall the basic points of Landau theory. So one says you have some complicated system, there is some order parameter. So you have to choose the order parameter M. And then one says that write a free energy formula, free energy as a function of M, consistent with the symmetries of N. So this is okay. Then I write f of M. In the Ising case, I write is equal to f0 plus m squared plus m4 plus, then it says ignore higher order terms. So it says something like Fm has a Taylor expansion in M, which is known to be false, because otherwise all these funny values of beta cannot occur. So the function is not Taylor expandable, but you Landau assume that it can be Taylor expanded, and then you get some set of exponents. Then one says that okay, the exponents are not right, but the general theory is okay. Don't worry about exponents, but at least the general qualitative features of the phase behavior can be reproduced by the basic Landau theory. Even that is not working in the 2 by 2 by 2 cubes case. You can always tweak the stuff, because of course there is in the end there is a free energy function, but it's a complicated function of several variables. And of course there is a free energy which is minimized by the correct answer. But you cannot predict the answer if you didn't know it beforehand, easily, or by simple-minded theory. So that is where I like to stop. It says 33 minutes. I'm sure that is wrong. But anyway, I have hurried through. But now if I add something, it will be only marginal comments. So you are welcome to read the stuff. I think I should give one more reference for hard cubes. For the cubes, I noted down the reference. Dipanjan Mandal, Kedar Damle, myself, and Rajesh. This is published in Physical Review E 2019, 99. 052129. So this paper has nice pictures, of the three-dimensional with a lot of color. I thought about it, whether I can project them on screen. So I have the pen drive, but I'm not going to do it. So, no, I think you can look up the paper, it is as good. And it would have been a disruption if I jumped between the projector and the board, and I'm sticking to the chalk presentation just now. You are welcome to ask some questions. Yes, sir. Yeah. Yeah. In one of the set of the states here, the between, so it is called layered. We have a layered disordered nematic. So layered disordered nematic. We didn't know what to call it, so no, it is nematic, but it is between layers there is no correlation. So that is metastable. So let us take the extreme case where you have layers which are in some X order or Y order. Okay, and this one, so the layers are decoupled with each other. They can be in any orientation. So if you make them disordered, and this system is of size L by L by L, then there is an entropy of disorder. Which is like it's L log 2. Because each of the state can be in two possible states, and if most general state is typically a disordered state. However, if these are aligned parallel, there is a free energy of alignment which comes from the fact that if they are parallel, then some Z rods can actually come, and they will be more often coming if these are parallel. But so that energy goes like L cubed epsilon, where epsilon is a very small number. It's kind of related to the density of Z bonds, but it's actually density of Z bonds to the power k. So it's a very small number. But for large k, this will be bigger than this. But in the cases we can handle, epsilon is not so small, and epsilon is still very small because it can be 10 to the power minus 2 for one side density, but we are working with k equal to 7, so epsilon may be 10 to the power minus 6 or so. And so in the cases we have this term dominates over this, we have L equal to 100. And so, yes sir.
So it's always difficult to take the language here, speak about it,
Yeah.
I would have called that phase a negative, what's the word? If you have disks that have a direction like that, when they order, and the nematic order parameter is negative, not positive. So here you say you have these things that are randomly oriented. There's a nematic order particular.
Okay.
Because it has no
I see. Okay, yeah, so, okay, very good. I think that's a good name.
So it's negative.
Direction is chosen, but it is the disfavored direction instead of the preferred direction. Yeah.
So one question was like you said in 3 dimensions you can do simulations like 60 cube. Is it lattices of size
120 cube like that?
Okay. Using same kind of similar algorithms.
Yeah.
Okay. Another.
Yeah. So 100 cubed is not the best, but there are moderately powerful computers at Chennai.
Like parallelizable, right?
Yeah.
So that's.
So we use a cluster, and you work for a few months and to get all the data. But it's of the time cluster of some 1,000 sites and a few months of CPU, which is not It's not the world record. But
Any other questions? Okay, so that was really a great talk. It's good to know that there are still very simple models with which have a lot of interest surprises and a lot of scope for doing like real rigorous work and also very accurate simulations. I mean, so let's thank Deepak for this great lecture.